Alright, we're going to talk about adding and subtracting matrices. First of all, a matrix is a rectangular array of numbers enclosed in a single set of brackets. And they can be used to represent or organize data. If you look with me over on page, let's see, 216. Someone has used a matrix to organize some data referring to their inventory of picnic tables and barbecue grills.
Okay.
Page 216. Okay. Notice the inventory matrix has 2 rows and 2 columns. It's 8, 10, 15. Whoops. 8, 10, I think 15, 12. And it's enclosed in a bracket. Now the bracket makes a difference because later on in this unit, when we enclose by just vertical bars, we're talking about a determinant. So when you see the brackets, you're talking about a matrix. Now matrices are classified by their dimensions. This has 2 rows and also 2 columns. Just so happens it's the same number of columns and rows. But when I think about a column, I think about a front porch. The columns that hold up the front porch are vertical, so think about them that way. And then a row goes this way. So if I wanted to make a matrix that was a 2 by 3, it would have 2 rows but 3 columns. So we classify matrices by their dimensions. And we always do rows by columns. The number of rows by the number of columns. So on the bottom of page 16, represent the June sales data in matrix S. Interpret the entry S12. That means in the matrix S, the row 1, this is the row, the column 2, what entry is there? Alright, so we go to matrix S, which is down there in example 1. We go to row 1, column 2, and what is there?
10.
In example 1 at the bottom. In that one it would be 10 that I've got on the board, but in example 1 it would be a 9. So what is element 2-1? Row 2, column 1,
15.
be 15. Okay. So matrices are determined or classified by the number of rows and the number of columns. Alright, you can perform matrix addition on matrices that have the same dimensions by adding the corresponding elements, which are elements in the same position in the matrix. Alright, what are the dimensions of this matrix? Rows and columns. It is a 2 by 3. What are the dimensions of this matrix? 2 rows, 3 columns. It is a 2 by 3. If the dimensions are not the same, the matrices cannot be added or subtracted. But adding and subtracting them is just about as easy as adding and subtracting integers, because that's all you're going to do. Now, this answer will have the same dimensions. It's also going to be a 2 by 3. So 1 plus 3, negative 2 plus 9, 0 and a negative 3, a 3 and a negative 9, a negative 5 and a 6, and a 7 and a 12. And that's all there is to it. That's simple. What do you think would occur that would make subtraction tough? What's the only thing we ever miss? Signs. Yeah, that's it. Alright, see if you can do number 2. By the way, what are its dimensions?
3 by 2.
It's a 3 by 2. Both of them are 3 by 2s. We have 3 rows and 2 columns. Alright, fill in the blanks. Alright, what are the answers?
Negative 15, 25, negative 1, 1, negative 2, 15.
Okay. Did you see the order that we did them in? You go across the rows normally when you're talking about elements. So if I was going to call out the answers to you on homework or something, that's the order we would go in. Alright, questions about adding matrices. They have to have the same dimensions. What if they don't? What if the problem in the book, and this is going to happen, is a 2 by 3 and this one's a 3 by 2. They don't have the same dimensions, you just write not possible. So when that happens, if they don't have the same dimensions, you just say not possible.
Is that just with adding?
Huh?
Like, can't you do it?
That's adding and subtracting. Adding and subtracting. Alright, the additive identity for real numbers, not matrices, but with real numbers, the additive identity is the number that you add to another number so that it keeps its identity. So that's 0, right? If I add 7 to 0, 7 keeps its identity, so we call 0 the additive identity. With matrices, the additive identity matrix for the set of all matrices n by n, what does that mean? That means whatever the number of rows and whatever the number of columns. If I had a 0 matrix, that would mean that 0 is every element, and this is common sense. If I added it to another matrix with the same dimensions, guess what I would get? That matrix again, because it is an additive identity. Now, the opposite or additive inverse of a matrix is denoted this way. You just do the opposite of A. Okay? What would you get if you added 7 and negative 7? 0. What would you get if you added A and its additive inverse? The 0 matrix. It'd just have 0 in all the elements. Alright, so let's look at this one. What are the dimensions of these two matrices? Rows by columns. Rows go this way,
2, 1.
columns go this way. Both of them are what?
2 by 1.
2 rows,
Or 1
but
and
2 columns, right? So this is a 2 by 2. This is a 2 by 2. My answer is a 2 by 2. This is the 0 matrix or the additive identity matrix. So this original matrix over here just gets to keep its identity. Both of these matrices, if you'll notice, these two are additive inverses of each other. How do I know that? Well, they're the same element, it's just one's positive and one's negative. One's positive and one's negative. 0 is the only number that's its only additive inverse. So my answer is the 0 matrix, which is also called the additive identity matrix. Questions about that? I mean, I think I could take addition and subtraction of matrices down in the 7th grade. They could do this, right? Not hard at all. Alright, if two matrices A and B have the same dimensions, so the same thing has to be true about subtraction. If they have the same dimensions, and I want to subtract them, all subtraction is defined by adding an opposite. That's how subtraction is defined. And so it might help you when you're subtracting so that you're not looking back and forth and back and forth. If you change this to plus and just go through and change all those signs. Now that's just for those of us, and I include myself there, who miss signs sometimes. I think that just about gets everybody. So what are the dimensions of these two matrices? How many rows and how many columns? That's not hard. How many rows? Rows go this way.
2 by 3.
They're 2 by 3s. Remember, columns are like those on a house. They're vertical. They're holding the house. They're holding the porch up. Alright, so then we just combine the elements. I've changed this to addition because I'm adding the opposite. Adding the additive inverse of this one. And so 3 minus 1, 2 minus 4, 4 minus 3, negative 1 plus 2, 4 minus 2, and 0 minus 4. What are the dimensions on problem number 6?
2 by 2.
2 by 2s. Alright, would you do that one? There's subtraction there.
Zero. Zero. -3. 14.
That's true. Because this becomes addition, and we change all those signs. So would it be easy to miss a sign looking back and forth? I think it can be. So that's why I would just suggest that you do that, but you don't have to. Changing the signs. All right. A matrix equation is an equation in which the variable is a matrix. You can use addition and subtraction properties of equality to solve matrix equations. We could also have ones where we multiply and divide, but we're not going to really divide with matrices. We're going to multiply by the inverse. Multiplication of matrices now is a lot more involved than adding and subtracting, and I didn't say it was too hard for you. I just said it's a lot more involved. You have to pay really careful attention. Alright, so this is an example of a variable matrix because this matrix contains variables. As a matter of fact, it's everywhere, isn't it? There are variables everywhere. And by the way, all these matrices are what dimensions?
2 by 2.
2 by 2. Now, if I took this out and made an equation that we're used to, what would I teach a 5th grader to do to this equation here? What would I do to both sides? Add 1. Okay. So that they don't magically think something happens here. I show them to do opposites, right? Well, I'm going to show you the same thing here. I'm solving for my W. I'm solving for my variable, which happens to be a matrix. I've got something subtracted in the way. So whether you show this step or not, still, I'll add it to both sides. Now these two are opposites, and we're going to give me the 0 matrix, so they're going to cancel out. And when it does, I'll be left with the variable matrix here. And then all I have to do is add a couple of 2 by 2. So 0 plus 1, just add your corresponding elements. 1 plus 1 is 2. 8 plus 3 is 11. 9 plus 2 is 11. You might say, well, what does that mean? Notice at this point, and I think we're about to talk about this, this is showing equal matrices. So we're about to see the equal matrices mean that they have two things. They have the same dimensions. Well, they're both 2 by 2, that's good. And that they're equal corresponding element by corresponding element. So what's W? It's equal to 1. What's X? It's equal to 2. What's Y? It's equal to 11. What's Z? It's equal to 11. Makes me kind of think of a system of equations where we were solving for more than one variable at a time. A little while ago I mentioned Kramer's rule. The sheet was missing, do you remember? Then I said it says Kramer's rule. That is another way to solve a system of equations. And I have to say, it's not any more difficult than substitution and elimination, or I like Kramer's rule. It's dealing with determinants, and we will get there in just a few days here. And so equal matrices must be the same dimensions and their corresponding elements are equal to each other. So this example 1 here is showing equal matrices. Both A and B are 2 by 2 matrices, and their corresponding elements are equal. Therefore, A and B are equal matrices. Negative 0.75 and negative 3/4 are equal. 1/5 and 2/10 reduces to 1/5. Those are equal. 1/2 and 0.5, negative 2 and negative 2. So that's an example of equal matrices. Now, notice we've got a lot of vocabulary, and that's why I ran this off to give to you. We've talked about the dimensions of matrices. We've talked about the additive identity. We've talked about the additive inverse. Equal matrices. Now we're going to talk about a column matrix. A column matrix is right here. It just has one column. Whoops. column matrix. By the way, if I was going to give the dimensions of this matrix, the number of rows by the number of columns, what are the dimensions of this matrix?
1 by 1.
A 1 by 1 just have one little element.
1 by 3. 3 by 1.
It's got 3 rows and 1 column, so that's a 3 by 1. Alright, now, this looks weird the way they've got this typed because it's got fractions in it. But this is a row matrix. It might be better suited if I just simplified. Usually they use capital letters to denote matrices. So that would reduce to 4, and that would reduce to 6, and that would reduce to 8. I don't know why they didn't reduce those, but this is an example of a row matrix. What are its dimensions? How many rows? 1. How many columns? 3. So a row matrix has 1 row. A column matrix has 1 column. Are these matrices equal? When they have operations in parentheses, of course that just means they're the operations. So 6 minus 3 is 3. Negative 8 divided by 4 was negative 2. 15 divided by 3 is 5. And 4 minus 4 is 0. So those would actually be equal matrices. They have the same dimensions. They're both 2 by 2s. And they're equal element by element. Is this easier than the last chapter? Or really the last 2 chapters? A whole lot? Alright, let's look at this one. What would you do to both sides to solve for the variable matrix? Since you've got added stuff in the way, you would
And sort out.
subtract. So why don't you guys do this one? I'll draw dollars for you. Alright, so she just subtracted this 2 by 2 from both sides. Those cancel. Give me the 0 matrix. If I added the 0 matrix to that variable matrix, I'd have the variable matrix. 10 minus a negative 1 is 10 plus 1. 7 minus 0. Negative 4 minus 2. And negative 4 minus 5. Do you guys agree? Alright, you do.
That's not what I got.
So what you got?
That's not what I got. And that's probably right though.
Where did you, which element did you miss?
I got all those except for 11.
Okay, so the very first one. Alright, 10 minus a negative 1. Did you put a 9?
No. Yeah, I did. I did put a 9.
Okay. You put 9, I was real concerned. So we're good now. We know we're going to add that. Alright, I don't know how well you can see these. But here they are, and maybe you can see them better here. And you know you can write anywhere. That's your packet, so you write wherever you want to. But these are equal matrices, and we're to find the unknown variables in these matrices. And so if these are equal, that means that 2x minus 5 is equal to 25, which we could solve easily. And of course 4 is equal to 4 and 3 is equal to 3, but it also means that 3y plus 12 is equal to y plus 18. Alright, so solve for x and solve for y, and we'll draw this for dollars. Okay, then you guys get x is 15 and y is 3.
C. I got
Questions?
I got it that time.
What are the dimensions of those two matrices?
That is a 2 by 2.
2 by 2.
I know that too.
Okay, let's look at number 2. If this 1 by 2 is equal to this 1 by 2, then 3x is equal to negative 9, and 4 is equal to x plus y. Well, wait a minute. I can't solve one equation with two variables. But if I solve this equation and find x, what can I do? Plug it in to find y. So do that.
What? Oh, I thought you
Very good.
Oh, which
Okay.
Do I still get $1 for it?
On the next one. All right. Any questions? Y is negative 3, so x is negative 3, so y is 7. We doing better now?
Yeah, I got that.
All right. Let's look at number 3. What are the dimensions of number 3?
2 by 2.
It's 2 by 2. Solve for x and y. This is Baker's. If I subtracted this from over here, that negative. Like I'm going to get my y's together, so I take this to that side. There you go. You guys agree with x is 30 and y is 2? Yay or nay?
Yay.
Do we agree? Okay. This next one, let me make it a little bit bigger. I believe it's on the next slide. Notice what's going to happen here. I'm going to have 2m minus n is equal to 15. I'm going to have m plus n is equal to negative 3. Of course, 8 is equal to 8. I'm going to have negative 4m plus 2n is equal to negative 30. That looks so much like those last problems we did. Now, with two variables, how many equations do I need? Two. How many I have? 3. All right, so which ones do you think, equation 1, 2, or 3, would you use with the what method? I think I'd use the first two equations
With elimination.
with the elimination method because why?
Because.
They're already ready, aren't they?
Yes, they are.
All right, so 2m minus n is equal to 15. M plus n is equal to negative 3. You're right, this is also set up pretty easily for the substitution method. And all I have to do is solve for m or n right here and ready to go. But these eliminate. 3m would be equal to 12. So m is 4. How is it that I find n? Remember?
Plug in on back in.
Plug it in. Alright, so that would be 4 plus n is negative 3. So n is negative 7. So all that substitution and elimination, you may have to use it again, okay? So don't just forget it. Throw it away. Don't do that. Y'all already thrown it away? Too late. Did that over Easter weekend, huh? Alright, questions? More vocabulary. A scalar, and notice that word doesn't have an E in it, it's not scalar.
scalar, I guess.
I say sky.
is a number multiplied by each element of the matrix. It's comparable to maybe a giant distributive property. So if this is the matrix A, and by the way, what are its dimensions?
3 by 3.
It is a 3 by 3. He's got it now. Of course, that was easy because they're by 3. What is what would be negative 2 times A? All you literally do is multiply each element by negative 2.
Yeah.
Any questions? So we can add, we can subtract, we can do scalar multiplication, but we can't multiply matrices yet, but we'll be able to do that soon, alright? Any questions?
I can
Now,
do
if you
that.
came back to the ACT and these were the problems, y'all would have, your pencil would have been smoking also, you know, without a calculator.
And then afterwards you move out.
Yeah. If you didn't know what we're about to talk about, it would just look very strange to you, but that it's not very complicated. Example 6, you see a quadrilateral, flashback to geometry there, we see a quadrilateral ABCD, and the ordered pairs are not listed horizontally like you would think, but actually vertically. Like, look in the matrix, P, and the point for A, negative 3, 3, is the first column. And then the ordered pair for the point B, 3, 2, is the second column. And then the ordered pair for C, 3, negative 2, is the third column. And then D is the final column. So when if you're asked to put the coordinates of any shape, whether it be quadrilateral, pentagon, octagon, whatever it is, you would just do the ordered pairs in columns. Does that make sense? Alright, turn to page 220, example 7. Now this is an application of scalar multiplication used in geometry. Did you guys do matrices in geometry?
No.
No? Okay, so let's say that we had that little red quadrilateral ABCD, and we multiplied the matrix P by 2, and then graphed those points. What happens? It doubles the area, doesn't it?
Yes.
Okay. On the other hand, on the B part there, we've got our little red quadrilateral, still the same one, and we do scalar multiplication by 1/2, and then we graph those points, A double prime, B double prime, C double prime, D double prime is the way you read those new letters across the new matrix. And what's happened to our original quadrilateral? It's been literally halved, hasn't it? It's been shrunk. Its area has been shrunk. So that would have looked weird, but it's not that weird, is it? All of the vertices are just listed in columns is all you do. Alright, go over to page 221. Number 5, represent the inventory data at the right in a matrix M. By the way, what would be its dimensions?
3 by 3.
It'd be a 3 by 3. Going across the rows, it would simply be 12, 28, 17 on the first row, 15, 32, 45 on the second row, and 6, 20, 30 on the third row. What would be the entry M23, second row, third column? Second row, third column. What would it be?
20. Wait, which
Go
one?
the second row, the third column.
45.
45. Okay. Alright, on number 6, you're solving for X and Y. On number 7, look at the A part and the B part. They gave us matrix R and matrix S. They asked us to add and then subtract. Number 8, it is possible to have more than one matrix, and as long as they have the same what, you can add and subtract them. Dimensions. And then number 9, you're using scalar multiplication. Number 10, you're going to represent quadrilateral ABCD as a matrix Q, putting the ordered pairs in columns. And then number 11, you're going to do scalar multiplication again. So do 6 through 11 in your notes there.
Oh,
hang
why
on,
not?
hang on just a sec. Alright, solving for X. He's only got X is 3, but over here, solving for Y. Y is -4. Okay. Questions? Are we good? Alright, number 7. A.
Yeah, but I'm confused as to how different.
Have you got this? Look like you do A, and that point is -3, so you would go because don't you go here? A, I'm looking at A. Oh, it's right here. -3. Oh, and then you do the same thing with B, like it's A, B, C, D. I don't know, let's look at this one and see if it's right.
Oh, you know
11, -7, -7, 5, 0, 6. You guys agree?
Yeah.
Go to the next page.
That's for that dollar right
80
here.
there.
He's being sissy testing me.
Go to the next page.
I borrow your book. I didn't know if it was.
Right.
I'm doing 7B.
7B.
So on that test I have to take, there's just consistent, independent, consistent, dependent.
Did you say inconsistent?
Maybe.
Okay, then maybe all 3 of those are on there.
I said inconsistent, consistent, independent, and consistent, dependent.
They're all 3 on there.
Is there more than that on there?
Yeah.
Or is that just the 3?
Yeah, there's like
You know that table that you and I were looking at earlier?
That, oh yeah.
That
that's what I'm
is the
talking-
summary of the whole chapter.
There's like 6 of them.
So that's everything.
That's everything. I got you.
Yes.
Alright.
Is this the pen? What is this pen?
That one?
Have you guys read this?
Haven't even looked at them. Since it was Easter, I didn't.
Too busy eating chocolate.
Yeah.
My grandma made some really nasty chicken casserole.
Wait a second.
I can send her a link.
I tried my hardest. It's pretty good.
It was horrible, but it was pretty good. You ate it, huh?
I ate it.
Alright, so 3 minus 8, 2 minus -9 is 2 plus 9, -5 plus 2, -1 minus 6, -7 minus 7, and 9 plus 3. Questions on those? Alright. Alright, on to number 8.
Avery's shirt's pretty funny.
I'll do some shit with that in.
Weekend too. That's funny.
For you.
Week starts.
What grade is this again? I keep forgetting.
I think two ones. Exactly.
Yeah, yeah. Second, I think that's about right. I feel sorry for some of y'all.
Yeah, it's okay. Trevor's rich.
You weren't one of them, Trevor.
See, I'm not one of those. I know I'm not.
Now, if you did the operations just all the way across, all at one time, or if you separated it out and did two at a time, either way is good. Any questions about that?
Can I go to the next page?
Please, yeah.
Oh, I can't see it anymore.
Guys. Good. Very good. Change it. All right, questions about that? Number 10. All we're going to do here is list our matrices in little columns. A, B, C, D. That's it. Now we're going to use that matrix to do 11A and 11B. All right, Trev? Let's multiply it by 3.
Did you even do it?
Well, of course it has. Making sure it's right.
Number 10. All right. 11, the A part.
Wait, what are you?
You can bring it with
What is
you.
3? Times
If you
by
can't
3?
remember times 3 times all those numbers over there.
Oh boy. Put this there you go. Sorry, I'm a tall man. Don't make fun of me, Jacob.
Oh, God.
Are you multiplying by 3?
Yeah, that's
Oh,
what it says.
okay. You're not yet. I got you. Okay. Prayer might be a good idea.
That's my idea when I stand up.
Trevor, that's wrong.
Why do they think everything you do is funny? I'm not sure.
No, we had
Shut up.
kids in the garden or any
All
class.
right.
Sorry, I'm a tall kindergarten.
11B.
You can't even read that, Trevor.
You part stupid?
So I can read that just fine. Hey, I like laughing.
Like, you want me to write out?
I just write the answer if I remember.
Okay.
Because it's right above there.
Okay.
y'all. Anybody have a question?